Today I'm going to talk about coupling effects on Polarization-Agile patch antenna arrays. I'm Chen, and Professor Chen and I are from Graduate Institute of Communication Engineering, National Taiwan University, Taipei, Taiwan. And Professor Jennifer T. Bernhard is from Electromagnetics Laboratory, University of Illinois at Urbana-Champaign, Illinois, USA. So this is my outline for today. I'm going to do a brief introduction on antenna coupling, and then I'm going to talk about the antenna elements that we use in our arrays, and then the proposed antenna arrays, which we propose 2 different configurations of our 4-element array, and then the results, which is the simulated performance of the arrays. So first, about antenna coupling. We all want smaller antennas for most applications, and when we try to bring each element closer to each other, the coupling increases. So before we try to design a larger array, we need to look into the problem of antenna coupling to know how the design is working. So that's what we're trying to do here. Now we're going to talk about the antenna elements. So on the left-hand side, we see a square patch antenna with half a wavelength side feeding diagonally from here. On the right side, we see a modified version of the patch antenna. This one is linearly polarized in this direction. And on the right-hand side, we add a little stub here on one side and put a via short to the ground. That way, we bring open, which is originally here, back to here, where there's a virtual open. So by doing this, and having these 2 paths have a 90-degree phase difference, we have a circularly polarized antenna. So to do polarization agility, we put the stub here for the left-hand circularly polarized one, because the wave reaches here first and then reaches this side, so it's left-hand circularly polarized. The other one, we put the stub on the other side, so it is right-hand circularly polarized. And now we replace the copper stub we have here and here, put them together, and place a pin dial here and here, so that when we apply our DC bias either on the patch or on the ground, we can switch on and off the dials, making it polarization-agile. So if we turn on D1, it is left-hand circularly polarized. If we turn on D2, it is right-hand circularly polarized. So this was a work we did last year at APS. This is the element that we're going to use today. The general idea is the same as the last slide. We feed from here. We have a couple of gaps to avoid the DC from hitting our RF. And then we have this. This is where we feed the DC, and the inductor is to avoid the RF from going into the DC. We have the via here. We have a couple of parameters like where the stub is, how long the stub is, and where we feed it to do a bit of tuning of the axis ratio and the S1 matching. So for the pin dials we use here, we use Skyworks SMP 1322040 LF, and its model looks like this. So we put this model into our simulations. And also the voltage for the dials are 0.8 volts. Our center frequency is 1.575 gigahertz, which is for GNSS applications. The board that we used is FR4, which has a dielectric constant of 4.3, and a tangent delta is 0.011. So we have the S11 matching like this, which is below -10 at our wanted frequency. And on the right, we see the gain and the axis ratio of the single element performance, which is about 2 dB IC gain and less than 1 dB axis ratio. So now we're going to get into the antenna arrays. We have 2 different configurations here. On the left-hand side, we have the corner-to-corner, which means we put it corner-to-corner. On the right-hand side, we have the side-to-side. You can see the difference here. So the size of these are actually, the left one, the ground plane is about 18 centimeters. That is 7 inches. On the right-hand side, it is about 21 centimeters, about 8 inches on each side. To make the performance better for circularly polarized, we use sequential feed, which was done by Professor P.S. Hall. So on the left-hand side, we see the left-hand circularly polarized one. We feed this antenna at 0 degrees. We feed this at a 90-degree phase difference. We feed this one 180 degrees and so on. So since 270 leads 180 by 90 degrees and 180 leads 90 by 90, on the left-hand side, the wave goes like this. So this is a left-hand circularly polarized one. On the right, we do the same thing the other way around, from 0 degree, 270, and so on. So it is this way. So that is a right-hand circularly polarized one. So now we're going to talk about our results. For the corner to corner, it looks like this. We do the left-hand circularly polarized and the right-hand one because they are different. For the left-hand circularly polarized one, we see that the stubs are overall on the outside of the structure, and the right-hand circularly polarized one are on the inside of the structure. So we anticipate the right-hand circularly polarized one to have worse coupling than the other one. So let's see the simulated results. So this one is the right-hand circularly polarized one. We see the stubs are on the inside. We feed 0 degrees to 170 and so on. On the right-hand side, we see the graph of the axial ratio and the circularly polarized gain. We did 3 different spacings, 0.35 wavelength, 0.4 wavelength, and half a wavelength. So for the 0.4 and the 0.5, the axial ratio is really low, just as we expected from sequential feed. The 0.35 is higher because it is way too close, like the tip nearly touches. So that is also kind of expected from the array itself. Without the simulation, we already know that the 0.35 is going to be worse. The gain, as we can see, the 0.35 is the worst, which is this one, a bit over 4 dBIC. The other two, 0.4 and 0.5, are around 6 dBIC. And this is the S21 and S31, which is the coupling coefficients. The S21 are the adjacent ones, the S31 on the opposite ones. So as we can see, the 0.35 is worse than the other two. As we can see here, the thicker lines are the S21. So the 0.35 are worse than the 0.4 and worse than the 0.5, which is pretty, like, that's what we expected because as they're further apart, the coupling should be less. For the S31, we see the lines here, which has a similar trend of being closer, being worse. This is the simulated E-field radiation pattern after normalization. So we see that it is directly this direction. Now we're gonna see the other one, the left-hand circularly polarized one, where the stubs are on the outside. So the same is seen here, that the 0.35 spacing is a bit worse, but axial ratio is 3 is like here. We aim below that. It also works, but the other two are way better. They're close to 0. For the gain, it is also like the 0.35 is worse than the other two, with the 0.4 and the 0.5 higher than the right-hand circularly polarized one because we expect lower coupling. So with everything working better, the gain is slightly higher than 6 dBIC. So this is the coupling coefficients of the left-hand circularly polarized one. As we can see here, it is not as clear as the other one, probably because everything is kind of further away. So it doesn't really follow the like the 0.35 is worse than the other two, but you can see kind of a little trend here. So this is the radiation pattern, also normalized. Now we're going to talk about the side to side, because for the left-hand circularly polarized one, the stuff goes like in this direction for every antenna, and the right-hand circularly polarized one goes on the other side. They're pretty much geometrically the same, so we're gonna just talk about one of them. So for the side to side, we also do the 0.35 wavelength, 0.4 wavelength, and 0.5 wavelength spacing. Because they are put side to side, when we have 0.35 wavelength spacing, they do not almost touch as the corner-to-corner one does. So we can see the axial ratio are very good for all three, and the gain is pretty much expected that the 0.35 is still the worst, and we see a little bit of overlapping there. 0.5 is generally better a bit than the 0.4 because like further away the coupling is less. Also, the gain is higher. It almost touches 7 dBIC here. So now for the coupling coefficients of the site-to-site design, everything is pretty much below -20. We cannot see very much difference between different spacings just because they're kind of further apart, even though the spacing is the same. Like the copper are kind of further apart. The difference between different spacing isn't that obvious here. This is the radiation pattern of the site-to-site configurations. So now we're gonna compare both. As we can see here, the left hand one is the corner-to-corner, the right hand one is the site-to-site. So we put them in a spacing of 0.4 wavelength, and we can see the S21, which is the adjacent coupling coefficients. The right-hand circularly polarized one is supposed to be closer to each other. So the general trend is the corner-to-corner RHCP is worse than the one of LHCP, and the site-to-site is the best. For the opposite coupling coefficients, it is not that obvious, probably because it's further apart. And also, this is the S11 of the two configurations, with this one having the left hand and the right hand. The S11 is below -10. This is the performance because we use FR4. The efficiency is 37% for single element. It is higher for the array. As we can see, the gain is also the highest for the site-to-site because they are further apart. These are all for the 0.4 wavelength spacing. So now, for the current work, we're working on also having the sequential feed design and not just using 0 degrees, 90 degrees. On the left-hand side, we do a loaded line to do the phase difference. And on the right-hand side, we do a meander line with a bandpass filter to block the DC, so that we can just apply the DC to the patch and then switch everything, including the loaded line and meander line path, and also the stops on the antenna. These are my references. Thank you for listening.